Hi, so good afternoon, everyone, or good evening, depending on where you are on the planet. Don't think we have any good mornings here. Um, so it's a pleasure to introduce Dr. Arijit Sen as our speaker today. So Arijit is a faculty member in the Department of Electrical Engineering and Computer Science at IISER Bhopal, and his research interests broadly span control, optimization, multi-agent systems, and robotics. So he got his bachelor's degree in electrical engineering in 2014 at Jadavpur, and then he got his master's and PhD also in electrical engineering from IIT Kanpur in 2016 and 2020. So after his PhD, he worked as a research associate at IIT Kanpur from 2021 to mid 2022. And his research interests lie broadly in control, optimization, multi-agent systems, and robotics. So his accomplishments have been recognized by Young Author Awards received from a number of organizations. These include the Control Society of India in 2017, the American Automatic Control Council in 2018, the European Control Association in 2019, and IFAC in 2020. So, Arijit, welcome. So, folks, we'll follow the usual drill. If you have any questions, you can just raise your hand or type them in the chat box. But we'll leave it to Arijit to decide if he wants to take your questions, in the middle of the talk, or whether he wants to wait till the very end. So, Arijit, over to you.
Yeah, thank you, Aditya. And yeah, I'm feel free if anyone can stop in between. We can. It will be nice to discuss. So thank you, Aditya, Sandeep, and Sujit for this nice for this invitation and this nice initiation of to have a weekly meeting where all this robotics and control enthusiasts can meet and discuss what is going on.
Yeah.
So this result is little bit old as I can say because mostly my I did something during my PhD and later part when I was in Kanpur and eventually when I just joined here. So some part I want to discuss and as I found that I am a very much I was a very I used to love to read mythological books and also just try to connect mythology and since mathematics is one of my used to be very comfort zone when I was in school. So again, we found something which is it can be discussed using some mathematical tools and magic is mostly just to catch the people's attention. As the name suggests, it's a Chakravyuha, the name we said, and we usually see this word, or we came across this word when we discussed, or when we studied Mahabharata, where Abhimanyu got trapped in Chakravyuha and he could not able to get out of it. And these mythological aspects, how we can, motivate our problem and how this mathematically we derive certain formula and results and then we'll see what happened when mythology and mathematics comes together. Is there any magic or not? Well, so just before going to this talk, is anyway, it is little bit older slide, so just ignore the first part. And obviously, the potential collaborators are always welcome. And Sujit and I work in some problems together. We'll try to solve some control and robotics related problem together. So these are the recent areas where we are working. So I'm much more into control side rather the robotics or AI or ML side. Well, uh, so as we know, we can see. So this is generated by Gemini AI. Since I'm not good person who tell more about this AI related stuff. I guess these pictures are pretty. I found these pictures are pretty nice when I give certain commands. So as we see, there are four kind of warriors. I put here in this picture. So from the leftmost side is a horse rider, and then one elephant rider, another person who is on the feet, and another person who is a chariot rider. So these four kind of warriors we used to see when we see nice old movies of wars or even in serials and daily soap operas. We can imagine that when the Mahabharata happened, whether it is we call some people call it history, some people call it mythology. So let's consider this in the mythological aspect itself. So in the ancient times, usually we see these four kind of warriors are pretty common in Indian subcontinent region. So either there are horse rider or elephant rider, some people on the feet and the chariot rider. So one basic, so these four people, if we see, they form form the formations of different kind of warfares. And one common thing we can address that except the person who is on the feet, all these warriors, even if whether there is on horse, they're on elephant or on the chariot, they can either move straight or they can take some turn. Right? Either they can take little bit right turn or little bit left turn, and mostly they can go straight. You cannot fight if someone attacks from their left or right. It is little bit difficult for them. They have to take a turn and then they need to see what is going on. It's kind of motion we in common days we defined is one of the very nice motion model we usually see, which is called unicycle model. Okay, so all this I'm just giving the example of the ancient warrior case. So these four kind of warriors were there utilizing this. Dronacharya built Chakravyuha to capture not only the Pandavas and other others warriors, and only Arjuna can escape through this Chakravyuha. So Abhimanyu can enter it, but he cannot break this Chakravyuha. That was the story. So what we see that utilizing the four kind of warriors who can either move straight or who can move either little bit left and right, utilizing these warriors, Dronacharya makes Chakravyuha to trap some enemies and all. So the question comes that, okay, as we said, that can we model the motion of such warriors? And we said that any vehicle which can take either go straight or take left and right. So nowadays we represent this kind of motion using unicycle. That is on our mind. Why Chakravyuha is one of the challenging formation in warfare, and can it be represented using some mathematics or not? Or can we get some control theoretical aspects uh, to just justify or to see what happened or why this was little bit challenging and how people get trapped and why it is important? So this was a mythological aspect what which built this area in my work which I did earlier. And based on that, we try to give the what is there at current stages. So this three so these are the tentative uh, outline of today's discussions. So mainly we'll see that although we give the mathematical aspect, but when with the current scenario or the academic scenario, so why the motivation comes, why we go for this circular formation, and why it is important and all. And there are a few results we'll discuss where mostly it will be spanned in cooperative localization of a target utilizing multiple unicycles. So as we said earlier that why I am considering unicycle, because all these motions of the ancient warriors can be expressed using the unicycle model, and some concluding remarks and how we can extend the same approaches of this information rich framework for multi-target problem scenario. So initially we will see for one target case and then we'll see what will happen or how we can extend the same thing for multi-target problem scenario. So so initial motivation of the mythological reference already we discussed. So now see why we call this mathematics part is there and the motivation was there behind it. Okay, so since those who are new to multi stuff, so if we see the our sky nowadays or even different natural aspects, you can see the flocks of birds, flocks of fishes are going here and there to move from one place to another place. And why this kind of species don't move alone, or rather they always go with a group or as a bunch or as a team. The reason is that sometimes they need to make sure that every person or every entity or every entity in that particular group can achieve certain things. So let's say if I consider a team of uh, or the school of flock, the birds are flocking, the flocks of birds are going on. So in such case, it is we used to see that they keep on changing their positions so that the younger birds they sometimes take the lead, and later on some older birds can be rested and so on and so forth. So as a whole, it seems that if when the multi-agent system is introduced, or if we introduce multi-agent systems in our work, the major advantage it provides that it improves flexibility and scalability as well in a system. How we can see from the example. So let me take an example of a football team. That if everyone is good, then what will happen if some person is got a little bit injured or someone's form is not good enough, then other can manage the other persons or the the person who is not doing well, his workload, his or her workload. So this kind of flexibility added when we introduce multi-agent systems instead of one single agent systems and all. And from control perspectives, although as I said much that I'm much more into control person, so the different application we usually see in such multi-agent systems in real world is like mostly the cooperative control. So in cooperative control means, as we discussed that, as we mentioned that instead of sending one particular uh, let's say drones, if we send multiple drones to monitor certain area or to take decisions or to transfer certain you know some medicines or some stuff, so in there this cooperative control helps a lot. And in addition to that, swarming and flocking, so again this example is much more related to drones and autonomous vehicles. And there is something, there is another stuff is like attitude synchronization. So attitude synchronization means uh, in our satellite setup, the attitude of each satellite need to be synchronized in a proper manner. So to make sure that some components of a satellite need to be synchronized in a proper manner. So basically the orientation of those components need must to be synchronized. So to obtain that, instead of developing any decentralized controller or one controller for one particular entity, if we can develop some multi-agent control technique, so it eases the control objective. And there is another is like distributed localization part. So this example we can easily see. Let's say multiple people are going at one place, and they can, so each person can localize himself or herself at one particular area, and then they can just keep on discussing among themselves just to know get a knowledge about the entire area. So one example we can see in real life, especially from robotics perspective. Let's say I want to map a big region. It can be an underwater, it can be in aerial place, or it can be a big very large area. So instead of sending one robot or one vehicle, I can send multiple small vehicles, and they will explore some nearby region. And as they approaches, as one of them will approach another robot or another vehicle, so they will keep exchanging their map, which is they already explored. And while talking to the neighbors, ultimately each of robots will so all of these robots will get the idea of what is the environment, what is the situation of this environment. And in addition to that, microgrid is one of the very nice example of multi-agent system where different islanded grid can be considered as one agent, and depending upon their power requirement, it can modify their voltage, so group and the other power generation component, so that the grid frequency and the grid voltage remain in the stable region. And in addition to path planning, multi-robot path planning is another very widely explored application in multi-agent system in there. Okay, so although we discussed about this applications and advantages, and so here I'll discuss mostly about this formation control stuff uh, in this today's discussions. So what is formation and why we need multiple formations? So it is found that in earlier of this century, that the migrating birds, they usually make a V-shaped formation. Right? It means if you see nowadays it is a little bit rainy season, we won't see nice sky, but usually before the winter, it is pretty. If you look at the sky, you can see that there are lots of birds are roaming from here to another places in the sky. So it is found that the migrating birds, they usually make this kind of V-shaped formation so that they can save their energy during a long flight. Okay, and the same thing has been experimentally validated using multiple aerial vehicles, and it is there also. It is experimentally tested that if the multiple aeroplanes make some tight formation, then the vehicle which are trailing, they can save a lot of fuel. So whatever observation or whatever means observation one have from the nature, the same thing can be actually experimentally validated using a proper aircraft, utilizing aircraft. So that is why this formation control stuff come into the picture. So if we can maintain some formation of different vehicles, whether it is multiple UAV or multiple robots, we can do some lot of stuff with eases. So here there are three applications I have mentioned here. There's where we utilize such formation control techniques in real life. So there are three very much widely used applications. Sometimes we need to send multiple drones to for the search and rescue mission, where one particular drone will be having certain cameras, another particular drone will have some other things to deliver and all. And similarly for the fire monitoring, so it is difficult to monitor if there is a uh, say in Australia or in US, I guess in last year or a couple of years back, the fire breakout happened. So in such cases, if you want to monitor that, what is the damage caused or where we need to minimize, how we can minimize the damage to get the knowledge about those information of those situations, how we can utilize drones or robots instead of sending our human resources. So here what we can do, instead of sending one particular drones or one particular aircraft or some helicopter or something like that, is we can send multiple drones and it can monitor different areas of this wherever the fire was broken out, and it can send the pictures or video, and based on that one can take a decision how to deal with those situations. Similarly for surveillance purpose, that if we have, for example, this airport or a very large area where it need to be monitored every time, whether it is a defense area, it can be a defense or military area or some very sensitive region of our country. So then instead of sending human resources, or apart from sending human resources, this mm, if we send any autonomous vehicle, they can also keep on capturing images of the border part and all to survey for the surveillance purpose. So these three are very common uh, applications of multi-vehicle formation, and to get so that we can get maximum information about whatever we are interested in. Okay. So now the challenges, as I said, that we started from the Chakravyuha part, and then it said something related to the application of multi-agent and so why this Chakravyuha or the circular formation and this multi-agent setup, how these are correlated. Okay, so it was found that it's about surveillance and tracking problem. It can be how we can go to, or how we can track a particular region, or how we can uh, perform surveillance at a particular region. So usually we fix one center point, or some area which has more where we give more importance to it, and we can consider this as a center. And easiest part is go to the center or go near to the center and keep on orbiting that region in a some, whether it is in a circle or elliptical or in some other geometry. Okay, so that is why this orbiting of a particular target or particular locations comes into the picture. That okay, first we need to locate where to go and how we can orbit those areas. Now challenges occurs. Let's say if I have a target, I don't know what is its exact position, because most of the cases the target will be coming from the enemy region or some, as we discussed, the some region I am talking about, like for example fire broke out happened, so we probably don't know what is the exact location of it. Okay, so either we can estimate using GPS and all, but if we are considering the real target where some enemy vehicle has entered in our airspace, then how we can deal it? So we need to measure those target position utilizing some onboard sensors. Okay, so that is why you need to localize it. We need to localize this target utilizing some noisy sensors available on the different kind of whatever UAVs or ground robots or other uh, agents we have for locating or performing surveillance tasks or tracking down this unknown target. And okay, so that's a main case, that we need to localize an unknown target. And later it is found that if we, instead of sending one or two vehicles, if we keep on increasing the vehicles or number of UAVs or even any autonomous vehicle, the localization performance gets better. Okay. But obviously, it has certain practical constraint as well. But we just cannot send hundreds of UAVs to localize one particular vehicle. But it's instead of sending one or two, if we say for say, let's say if we send 5 or 6, definitely the localization performance will get improved. So later there is certain works by Bishops and group. They have established or they have give some results where it's that something is called optimal sense. So it, as we discussed, that we need to maximize the information. We need to know more about an unknown target. We need to localize an unknown target more efficiently. How to do that? So it says that if we can make some optimal formation of different use of different sensor, it can be speed, sorry, velocity, but not velocity. It can be position sensors, two major positions like range sensor or bearing sensors, and so on. So if those sensors, if we use, and if those sensors make certain geometry in 2D, then the feature information of the entire system will get increased. So what is feature information here? So feature information says it's an inverse of uncertainty. So it means it says that let's uncertainty means I have less knowledge, or I am more. If you can say okay, I am uncertain about this area, it means I have less knowledge or less information about a certain area. As the uncertainty reduces, what happened? I become much more knowledgeable about those areas. So similarly, we can it is it implies is that uncertain reduction of uncertainty means the information is maximized. So Fisher is one scientist. So he developed this theory, which is called the Fisher information theory. So it says that even if I one can try to maximize any sorry, minimize the uncertainty and maximize the information, but still you cannot achieve infinite information of a certain region, or you cannot reduce your uncertainty to zero. So there will be always a lower bound in the uncertainty, and there is always a maximum bound of information. So this maximum information is called the Fisher information. Okay. So Bishop said that okay, if we put our sensor in a certain geometric formation, we can maximize the Fisher information in a multi-agent system. So during these processes and all, the different kind of target localization techniques have been studied by different uh, groups, whether it is a stationary target or moving target. Definitely the moving target is much more challenging stuff, and there are different kind of methods have been utilized. So I'm telling this is a little bit pre AI era. So during that time, the trajectory optimization was one of the very well-known approach, where these multiple agents optimize their trajectory around the target in such a fashion that the localization gets improved. And there is another approach, like it's called information guided clustering. Although I'm not well aware of this area, especially this information guided clustering part, it's mostly that what I have understood after reading, that is like wherever the maximum information is there, I'll send my group of UAVs in that particular region. So basically, I need to guide the cluster of UAVs in such a manner that information gets maximized. Okay, so these methods have been widely studied, and people are keep on uh, exploring those things. Okay, and so what was missing till during that time, that how there was no such common framework which can address everything, whether it is a Fisher information matrix maximization or control and other stuff. So let's see what we can do based on that. So that is why we thought that okay, can we make some unified framework which can handle everything? So to propose this problem, we consider an unicycle model in 2D. As we discussed earlier, the unicycle model is when we talked about our this ancient warriors and their motion. So unicycle model is mostly like it can. So if I consider this particular triangle, so let me consider this is a unicycle agents. So either it can go straight or it can take turn left and right. Okay, so it cannot go left sideways. Okay, so one of the very common example is fixed wing aircraft or fixed wing UAVs. This is one very popular example of unicycle vehicle. Okay. So we considered unicycle vehicle in 2D, and we assume that each agents or some of the agents are carrying range, bearing, or speed sensor to measure the relative information or relative range and bearing and speed with respect to a target. So this is my target P, and this is my agent I. So this range, this bearing and relative speed, this can be measured by one agent. It may possible that in multi-agent systems that one vehicle is carrying one kind of sensors, one can mean some group of vehicles is carrying range, some group is carrying bearing, some group of vehicles are carrying speed, but ultimately when they are cooperatively estimating the target position, they can they able to track or can they able to maximize information or means whether the information get better or the localization get better or not. Okay, so that was the initial thought. So based on that, we broke our entire objective of our work into three parts. That first is okay, let's maximize the target information. So when I can say that my target information is maximized, when we can get some formula or some nice optimal geometric structure of the multi-agent systems. Now, once we know that what are this optimal formation geometry, our main objective is to develop some control algorithm so that this geometry is achieved. So that was the second part. And third part, obviously, we need to localize this unknown target. So how we can do it? We need to develop some cooperative localization algorithm so that this estimation error is minimized. So these three objectives we try to solve, and based on that, we kind of this kind of since I'm a control engineer, I always try to represent any problem using block diagram. So we thought that okay, the entire problem can be sub-categorized into this kind of block diagram representation where the optimal formation geometry will derive from Fisher information matrix and it will be fit to the cooperative protocol. And as we know, the unknown target, it also getting some noisy measurement of this unknown target. And then we'll run some extended information filter to estimate the target positions and all. And definitely the control algorithm will take care of. And eventually, as a resulting, as it keep on doing, and as we know, the control engineers are as C approaches infinity, fine, all will be good. So, uh, so that was the proposed framework in this cooperative setup that we go for this optimal sensing. We will develop distributed controller algorithm, and we'll develop a cooperative localization technique so that ultimately we can efficiently localize a target utilizing a group of unicycle edges. So that was the main object. Now, as it has three parts. So the first part, as it said, get the maximum information of the target. Okay, so I'm not going to the mathematics in detail. So I'm just give the overview how we tried to solve it and what is the beauty of mathematics to solve some nice engineering problem. So in this case, as we discussed, that we consider something called heterogeneous sensing network. Heterogeneous means we consider that okay, some agents sensor, some agents may have bearing sensor, some agents may have speed sensor, and their variance or their type can be that is the heterogeneous means the type of the sensors and their quality can differ. Okay, so utilizing this heterogeneous sensing network, we try to estimate a moving target. So as we said, the moving target, and we consider the 2D moving target. So that is why what are the unknown quantities? One unknown is the positions of this target and the 2D velocity. So this four information we need to estimate. So to do that, there is, as we said, we need to calculate something is called Fisher information. So it has a very nice formula that although the agents are there, as we know, there is some sigma is going on from I to n in the multi-agent setup. But ultimately, this F is called as Fisher information matrix, and this Fisher information matrix or the order of the Fisher information matrix will become 4 cos 4 here, as this 4 is nothing but the number of unknown which we wanted to estimate. Okay. So it has a very nice, well-structured formula how we can, and mostly we utilize the Jacobian of the measurement model and do some algebra to get a expression of this Fisher information. Now, what challenges occur? What challenges occur here? So as we know, there is a summation over I from 1 to n. And the when we calculate the Jacobian of a particular sensing the sensor model, it has different cosine and sine terms. And as we know, this the sine cosine term, these are the nonlinear terms. And in addition to that, we have summation terms. So mostly we can consider that we are taking, so each element of this 4 cos 4 matrix has some summation term of different sinusoid components. So it is very difficult to visualize how to maximize or how we can interpret this Fisher information matrix to get a nice structure. So that is why initially we thought let's go for the trace. So why go for the trace? So when we say that we want to quantify a matrix, either we go for the trace or determinant, or sometimes the two norm or Frobenius norm. So mostly people go for either trace or determinant. And as we know, so determinant calculation where each element contain this sigma terms and sine and cosine terms is a little bit challenging. So being as so I was keep on saying that control engineers are the laziest engineers. So that is why we thought that calculating the trace first. Okay, so if things went well for trace, then I was I would become the happiest person. But unfortunately, what happened when we calculated the trace of this Fisher information matrix, all these terms get cancelled, and it gives a very small structure. And it is found that this particular variable or this particular expression, it doesn't depend on the formation of the multi-agent. So next step is, okay, we have to calculate the determinant of this matrix. As I said earlier, that the calculating the determinant of a 4 cos 4, although it is a 4 cos 4 matrix containing all this summation over sine and cosine, it is pretty much difficult. So that is why we consider two standard formation geometry. One is the target centric fixed formation. So another is target centric circumnavigating formation. So fixed formation means here the relative velocity with respect to the target and each agent is always. Whereas for circumnavigating case, it says that with respect to the target, each agent is rotating around along a circle with a constant omega or the angular velocity. These two standard formation geometry, which are very well studied problem and very well discussed approach in control theory. So we thought that okay, let's go with these two cases and see can some nice structure or not. And it is found that for both the cases, if we simplify the determinant, ultimately we get this kind of conditions need to be satisfied, where basically some summation over cosine and summation over sine terms need to be zero. So, and both the cases, the solution is same. That was the one of the very nice result we obtained, that although the formation is little bit different, but their motion is little bit different. In one case, the relative velocity is zero. In another case, the relative velocity is actually like it looks like that agent is circumnavigating the target with a constant velocity. But however, in both the cases, the maximum obtained or the determinant of the Fisher information matrix will be maximized. The conditions remain the same. Now next question come, okay, although we got a very nice, it looks like little bit nice expression, but it was not so when we was deriving it. So although we got a relatively nice, how we can visualize in real paper or in the real 2D plane. So there it is that the expression of this psi I, so which is relative, sorry, not relative, which is the bearing angle with respect of the target with respect to the agent, and this thing, and our the inter-agent angular spacing. So if we consider I and I plus 1 are two consecutive agents, so their inter-agent angular spacing subtended at the in the target, and this bearing angle, they have a nice geometric relationship. And utilizing this relationship, it is found, it is calculated that whatever formation geometry we obtain, ultimately we can ensure if all agents can match multicircular formation in both the cases, then the information of the entire multi-agent system will be maximized. Okay, so the first part is done, that we know that okay, we need to achieve a multicircular formation around a moving target, and it will give me the maximum information of the entire multi-agent system. Okay, now what question comes next? To obtain this multi-circular formation, we need to make sure that the radial distance with respect to target can be controlled. Second, inter-agent angular spacing need to be controlled. Third, which is the major important part, that ordering of the agents need to be controlled. So for example, here this 1, 2, 3, if we see, this order need to be maintained in a proper. Otherwise, we can we can get some nice formation, but not necessarily the information maybe information although it's maximized, but it won't be it become uncontrolled for our case. As we know that being a engineer, our main objective is my system should perform as per my wish, not as per some other mathematical tools wish or some other constraint. Okay, when we started discussing or started working on it, so these three challenges were there: how to maintain, make sure this all these three components need to be can perform as per our way. Obviously, the radial distance should be matched as per whatever, based on whatever desired we achieve. Second, angular spacing. Third, obviously, ordering. Okay, so during that time we referred some existing papers and all, and we found that there are some challenges are there. Means either the works they consider very restrictive or conservative as assumptions on target. Either it can be a constant speed or its angular motion is bounded, and so on. In some cases, they in the later or the most important work in these areas where the multi-circle formation was achieved. So in that particular work, it was found that okay, the system can get or can ensure multi-circular formation, but their interagent angular spacing can be any arbitrary. And why it is there? Because as unicycle model is a nonlinear system and as well as non-holonomic system. So depending upon the initial condition, the interagent angular separation at stated state may. And in addition to that, there are some coupling factor they have introduced where the coupling factor cannot be set as in that particular coupling factor actually come in the denominator of the steady state tracking error. So that is why we always we always get that the tracking error is non-zero as t approaches infinity. Okay, so these two are not were the most recent or the most popular or the most well studied uh, paper. Then we thought, okay, how we can achieve it, and we try to solve it from okay. Let's can we get some there's a can we get those in simple geometry or simple mathematics which is involved with geometry, nothing more than that. Okay, so that gives us this to draw this kind of uh, figure. So I'm not going into detail with this figure. So let look these three triangles for the time. So the black one is the target where which is moving arbitrarily or with some executing some maneuver in the 2D, and this blue one is my desired position. Okay, so if so, it's as the control engineer says. So if everything goes fine, uh, the state should match with this desired one. So this is my blue one is my desired position, and the red one is my basically the current of my vehicle. So our objective was how we can develop an algorithm so that or the control law so that this particular red dot or the red triangle will go to this blue triangle so that the tracking becomes that steady state tracking error. Utilizing this geometry, we derive from very simple second order different using different differential equations and all. We derive entire desired state. It should be the desired position, it should be the desired velocity and all. And it has this kind of expression in it. And the next step was once the desired position is there and we know the current position, what we do? We calculate the error dynamics. And as we say, the error dynamics also contain non-linearities and cross terms. So for example, if we see the x component contains y coordinate and y coordinate contains x coordinate plus cos theta sin theta those terms as well. Okay, I need to be a little bit fast. Okay, so this dynamics we got and how to minimize or how to make sure this errors goes to zero. We have two control input. One is v, which is forward speed, another is omega, angular velocity. So you need to design this vi and omega so that all this. So setting upon that, we develop this distributed or multi-circular circumnavigation protocol. We divide the again this entire control objective into two parts. Again, the first part is some distributed observer, and second is decentralized tracking controller. So, what are the distributed observer? As we know that in multi-agent setup, with the agents need not to be. It is not always that they know what is the desired parameters. Okay, it may possible that some agents know certain parameters, some other agents know some certain parameters, and so on and so forth. So here also we consider that okay, some agents certain approach, some agent may know some other stuff, and they will run a consensus protocol so that everyone they should achieve. So this estimator we design, and later this estimator will be fed to a tracking controller which is running on the each agent itself, and based on that ultimately the control execution will be done. And in this two that to know the desired parameter, we develop a fixed time control, fixed time protocol, where the advantages of this fixed time protocol is that competition is very high. Still, the convergence will be ensured within a specific time boundary. Okay, so the upper limit of this convergence time, as we see, this is a constant. It doesn't depend on the initial condition. Is to estimate different target informations and desired parameters, and later on the similar approach, consensus approach we utilize, where uh, as we discussed earlier, that one of the major challenges to make sure that intelligent angular spacing is as per our desired choice. So this estimator is utilized to estimate the intelligent angular spacing or to fix the intelligent angular by each individual agent. So in this case, we assume that I minus 1th vehicle knows the knows sorry ith vehicle knows state of certain estimate of its previous one. So basically, if agent 2 is there, it knows what is happening at agent 1, and the one cyclic graph is keep on following. And then based upon that, we assume that okay, the intelligent angular spacing can be set as 2 pi by n minus pi. Okay, so this var parameter. So earlier in some places, in some work, they ensured the regular
Yeah, is it
poly.
like maybe if
Sorry.
we can finish in 5 minutes?
Yeah, sure. It is
Yes.
almost ready. Okay, so those things are there. So this tuning parameter add us some more flexibility. Okay, so you can control this tuning parameter or set accordingly to get what is the intelligent angular spacing. So once this part controller and it looks pretty dirty. So one is obviously the angular velocity and linear speed. One can ask that how did I get any Akashvani or all of a sudden I wake up in the very morning and design it? It's absolutely not. So thanks to Lyapunov, so we utilize the Lyapunov technique to develop this controller itself, nonlinear controller. And one of the advantage of this controller is that as we can see, so this component in let's say Vi I am considering, so this component is always less than 1. So even if your position error is pretty high, still my requirement of the linear speed remain bounded. So as the angular velocity as well. So you know that this is saturation function sine function, and again some fractional terms are there. So this additional nonlinear, this additional nonlinearities are incorporated. We want to make sure that our control input doesn't overshoot. Okay, so utilizing this factor, we track down our controller. We make sure that our uh, unicycle agent will reaches to the desired position. So the second part is done. So first part, we know the conversion matrix, we know the geometry. Second, we came to know with design how to design those control algorithms so that all to those desired formation geometry. What was the next part? I'm escaping this simulations result part. Next part was we need to localize my target. How we can localize this target? So to do that, we actually uh, broke this EI or extended information filter in a cooperative manner, where agents actually in their update state. So prediction state for each agent is pretty straightforward. Whatever is their own state, they depends on that. But update states for the update, it keep on incorporating the neighbors measurement as well for update the neighbor its own state, and as well as to update the state of the target. So this is the way the cooperative is, and it is found using these simulations and all. The as we know, these two errors goes to become bounded, and it becomes very less for the position error. And this particular plots actually shows that filter and true data means what was the true value of the feature information, which is the determinant of the maximum of it, and it is found that it is almost tracking it perfectly. So here I have this video. Give a second. Yeah. So, okay, so this center part is my unknown target, and remaining guys are the agents. And please look this green circle. So it looks like a green circle, but it is an ellipsoid. An ellipse, we can say. Green part is the error ellipsoid. So it means that initially the error is pretty high, and as we see that as time will approaches and the formation, the agents keep on tracking the desired formation, the size of this green dot will reduce. Okay, so if I just so now this formation is achieved, almost they make a very regular polygon of or regular shaped circle. So now I go a little bit far. So if I go a little bit far, so now you can see that this area of the green is pretty less as compared to if we go back. If we go back, initially it was pretty high. So it means that as time approaches, the error becomes. So I'm not discussing this, but so later we actually try to formulate the same setup, the multi-agent instead of one target. If there are multiple targets are there, what we'll do? So to encircle multiple target, what is the easiest way? The easiest way that okay, just find the centroid of the multiple moving target. This we actually said that okay, how we can get it? So if we just look, yeah. Okay, so let's say if we consider that okay, multiple targets are there, you want to encircle multiple targets. So easiest way, let's consider the centroid of it and consider the maximum radius is required or the minimum radius required to encircle the all those targets. So how to do the same thing using a distributed algorithm? So those parts be taken care by a distributed average tracking algorithm, where if the targets, if, for example, here we considered 4 targets, if each agent has the knowledge about one target and those targets are moving, can we track the average of those time varying signals? So answer is yes. So there are some methods we had and we got some good publications from it. And second, or can we get the maximum of it? So here this global maximum tracking problem can be solved. So basically how we develop some algorithm so that we maximize the L infinity norm of a particular multiple signals in a distributed manner. So utilizing these two algorithm, we can actually encircle the multiple target as well, utilizing multiple unicycle. So I'll stop here. So I'm open to any question we have. So sorry for a little bit slow start and it got a little bit fast later. Okay.
No worries.
Thanks,
Yeah.
Arijit.
Thanks, Arijit. Thanks a lot for
Thank you
the.
everyone.
Okay. Hi everyone. So we are open for questions. So if you have any questions, please unmute yourself and go ahead. Or you can raise your hand. I can.
Okay, Arijit, I have one question.
So good.
Sure, Sujit, you can go ahead.
Okay, so how can we take care of localization uncertainty or communication packet drops in these frameworks?
Okay, so in this case, we did not consider the local means localization part for the communication packet drop. So okay, so let me just go here, give it back. Okay, so if we consider as we can model this weights of this graph in a time varying fashion, and when there is no signal is coming, we can set these things as 0, and instead of considering the graph is fixed with respect to the time, we can consider that okay, it can be a time varying graph, and where the weights of the edges can be 0 as well. So that can be done, but again there are some assumptions need to be there as well, considering that graph is connected for be jointly connected, or if we consider an infinite horizon, then the union of the graph is connected. So for there we can model those things, but however as of now in the real in application wise I have not seen those aspects. But for the time being, means we discussed something, we developed something where the graph is switching, which can represent this if there is certain communication loss will get lost. If there is a communication or link failure is there, communication link failure is there.
Okay. Thanks, Arijit.
Thank you. Thank you.
So, Arijit, I have a question on related. I have a related question, but on sensor modeling or like sensor noise that can come into picture. So, like in standard, we had these errors, right? Like, but then how do we validate this? Like, how do you validate these models exactly on real systems? Like, that's where I feel it hard. Like, even whatever sensor model I build, like modeling it on a multi-agent system becomes pretty hard, or validating it on a multi-agent system becomes pretty hard. Like, how do you go about it?
So, in this case, what we considered here, we considered doing standard sensor model which are available, like range, bearing, and speed. Some agents are carrying certain range and sensor. But when I guess your question is like when we deploy all these sensors multi-agent framework, how we can do this in real life, how we can use it, right? Is it so?
Yeah, kind of. Like, how close is this sensor model to the real world, real sensor that you use, or how do you validate that on a multi-agent system also? Because your sensor errors like that you model here will percolate into your navigation also, right? And your planning.
Mm-hmm.
So how close is it? How do you validate that this model is right for the system that you're using, or like right for the sensors that you're using?
Okay, so for example, the range sensor, what we consider is like it is pretty much standard. I guess the speed sensor was a little bit challenging stuff when we initially thought, but as of now, I do not have much answer in that. How means regarding, I have not tested this from the speed sensor perspective.
Okay.
But for bearing and range sensor, we utilize camera to get some information and just to estimate the bearing.
Mm-hmm.
But as you know, the image processing techniques takes more time and all as compared to a normal bearing sensor. So that is why while implementing that to even a very not even the moving target case, it's like we installed 2 or 3 robots and one stationary target. We just we are estimating the bearing and trying to get this estimation and all. So there actually this kind of whatever I this kind of framework is cooperative EIF. So it works. But for speed, I do not have knowledge as of now because I have not tested. So and that too, I don't know if even any student of my supervisor they did it. I have not done it yet. But for range and peering, we did it, and it was performing well. But one catch was that in the simulation, the frequency of the to feed this sensor update was pretty high. However, if we go with that in real life, it was not performing well, and there was some error. Error was pretty high. Means initially when we tried with considering the frequency, it's like every 3 steps there will be some data will be fed. Later on, I guess it is like that after 30 seconds, the bearing and range update will be incorporated in the EIF. So then it performs well. In a indoor case, we have not tested those things in outdoor.
Thanks. Any other questions from audience? Okay. Aditya, are you asking question, or I saw you unmute?
No.
Okay.
All good.
Yeah.
All good.
Thanks, Arijit, and this was a great talk. And
thank you for this.
I had one more question on adversarial. Like, have you thought of adversarial agents being part of the team? Because that's one of the problems like some of my students are interested in. So I thought, like, have you thought of that, or like, do you have any good references? Please share. Yeah.
Paper by John Leonard probably
John
regarding the
Leonard.
open. Yeah, probably the John Leonard or Naomi she presented something as a plenary talk. So let me just stop sharing it.
Sure.
Yeah. So she topic in I think 2023 CTC in Singapore. So one of my friends, he was visiting and so he actually asked me to read something. I'll check because there are some.
Please share it if you find
Yeah,
some.
and there is a group in Kanpur, Twinkle Tripathi. So she was. I don't know whether they are still working in this problem or not. I saw some of the papers. I think in ECC or ICC, those were accepted 2-3 years back. And I asked some of the students to read that. Anyway, it did not go in that direction. So where they assume that there are some agents which are mainly basically divided into two classes, protagonistic and antagonistic, and depending upon the sign of the weight, some are positive, some are negative. Ultimately they reach a particular point, they are reaching to two different opinions, and instead of one cluster it is like two clusters are forming. So they have some initial work, and nominal papers it has some work, but I have not pursued it. I read something that later on I pursued. I have not pursued. I'll check.
Thanks.
And if you are interested, we can discuss things. I found this problem is very nice, but somehow less explored.
Sure. Thanks. Okay, then let's thank our speaker, and thank you, Arijit, for taking time.
Thank you.
It was a great
Thanks,
talk.
Arijit.
Hi, thank you, Arijit. Thank you, Sandeep. Okay.
Thank you.
See you.
Thank you
Right.
everyone for joining,
Thank you.
and we'll see you again next week. And we have more speakers coming, and we have more talks in line. So hope to see you all next week. See you. Bye. Thanks,
Bye.
Aditya.
Bye.
Thanks, guys. Bye.